So we will be going to our follow-up presentation first, which is titled Using the Chemistry and Reactivity of Halogenated Rubber Oligomers in Identifying Unknown in Extractable Studies, which is presented by Lothar Habel, PhD Technical Advisor for Nelson Labs Europe. So hello there, Lothar. Welcome. Thank you for joining me today. And my name is Marcus. I'll be today's moderator. So before we begin, I'd just like to inform our viewers that we will be having a live question and answer session later. So please feel free to send in your questions for Lothar and for Daniel later via the questions tab, which is located directly below your webinar screen. And we will look forward to answering your questions later. Okay, and now please allow me to introduce our first presenter today. So Dr. Lothar Habel joins Nelson Labs Europe in December 2006 as a study director for extractable and leachable projects. And from the beginning, he directed his efforts towards parenteral and injectable applications, including rubber compounds, a field in which he honed his expertise over several years. And in 2023, he transitioned internally to the position of technical advisor. So Dr. Habel began his academic and professional career with the small-scale synthesis of organic chemical compounds, subsequently dedicating several years to research projects at universities and private enterprises, both in Germany and in Belgium. Okay, now with that, I'd like to hand over to our presenter today. So welcome, Lothar, and let me bring your slides up on the screen here.
Thank you for the introduction. So I will immediately start. Hopefully you will have no further problems with that. What will that be about, my presentation? It will be a bit, let's see if I can, I will talk a bit about our observations in controlled extractable studies on rubbers, and that meaning that it will be a special case of that should be in advance to my presentation. The contents will partly be a bit of the chemistry of the cross-linking, and after that I will introduce you and give you the results of our Nelson Labs Europe R&D program. That is that. Okay. What did we see in controlled extraction study on rubber material is that there are still a lot of unknown compounds. The stronger the extraction solvents, the more of those unknown compounds can be expected. If you see those unknowns in a chromatogram, or if you see that in an extraction profile, then you know already you have problems with it if you try to do a toxicological assessment on those compounds. If you go further, let me see, I have to go there, sorry. If you see, for instance, such a profile, like the example on this slide, you will see most of those compounds can clearly be identified. And even if they are there at high concentrations, that's no issue from the toxicological view on that. Only if there are some unknowns, they can be even at a small concentration. But of course, your toxicologist will tell you, well, that is still a big issue because it's even if it's a low concentration, it can be a compound with high toxicity, and that should be evaluated and simply handled as a compound with the highest level of concern, meaning the lowest allowed concentration in your extraction. So to give you an example of that is this extraction profile. This is one that we found in an older study, but it's very common, such an extractables profile. And we see that it's an UPLC-MS list of data, and one of those compounds is only partly identified, meaning you see but you see there's such a typical fragment, that N4S2 part. in it. Well, we have seen that, we have spotted that in the past, and we thought, well, that should be something very typical, because we've seen that in former studies already, and that can be something that is linked to one of the compounds we already know. And then we went to our database and made a simple search on that compound, that part of a compound, and our database is quite big. And then we see, well, that can be linked to that kind of cross-linker, simply by looking up that part of the structure, or meaning that part of the formula that's in there. Okay, what did we do next? We tried to find out where, well, we had seen other masses. It's that part in it, but other formulas are in there, but the masses, they didn't fit. But how can that compound have been in reactions that we can come to that mass? And then we made a simple, very easy arithmetical exercise to find some plausible compounds, meaning we used the formula of the base structure and added some other formulas, and we easily came to a structure that looked like that on this slide. Okay, this one that is in the middle, that is a known cross-linker, and the other ones, they are rubber oligomers. Rubber oligomers. So for that purpose, I think we should have a little exercise that's going a bit to the side of the topic. We concluded first, there must be some adducts possible of those compounds with those masses. And we found, normally you should know those brominated rubber oligomers from the previous presentation already, but I will give you some more insight in that. And for that purpose, we doing that exercise or that excursion into the world of rubber chemistry. That's very briefly, of course. So if you see to the normal vulcanization process of a rubber compound is always a two-step reaction, meaning first you make a polymer, and the second step you make the cross-linking. For the polymer, you expect that there are some reactive sites. If you see here, it's some kind of allylic bromide or vinylic that is supposed to be reactive for the cross-linking reaction, and then you have a certain cross-linking compound that will be used to make the link between the two polymer linear polymers. Well, you do not always have the full polymers that is there, because that is essential, of course, for our investigation, because you will not be able to put that in an analytical instrument. But you always find some kind of smaller fragments, meaning those little C13 fragments, and also you have the same principle with C21, but they can react the same way with the cross-linker as the polymer itself. But what you get are smaller compounds that can be detected with our instruments, potentially at least. And if you look at the C21 compounds, it's essentially the same. They can react the same way, but of course you get other masses, other heavier molecules, but the principles is still the same. And what you see then in the reaction product, meaning that what you can expect then is something that is very similar to that what I introduced in the beginning. So what we did is that we started up a research and development program. Well, what we did is, wait, I have to find that. Okay. What we could do was our expectations were, if we would find some oligomers that would be reactive with the compounds, the expected compounds, and that must be possible to simulate that on a small scale with simply extracts that we can generate a different way. And by that way, we would be able then to have a proof on the compounds we found in the extractable studies. So we started quite broad, I think. We decided to isolate the oligomers, the small oligomers, meaning mixtures of the C13 and the C21 fragments. But of course, the reactive part of that with the bromine, both on that. And of course, also a mixture, because we didn't want to make completely artificial compounds or mixtures, because we want to see, would that be possible in real life? Could we reproduce that in the real world of production of rubber and cross-linking of rubber materials? For that purpose, we further selected 10 vulcanizer or accelerator compounds for the reaction. And then the next step should be, well, if we made that selection, we should have a proof that the reaction conditions are appropriate to make the reaction finally. Okay, so we started with 4 different mixtures, meaning in the first vial that was a pure blanks mixture, meaning we took none of the oligomer, meaning that we only had the crosslinker and accelerator, and that is the first blank then, the vial 1. And in the second blank, we had the same mixture, but then we heated that as it would be in the curing procedure in the normal production of rubber products. Vial 3 is then that we added some of the oligomers and kept it at a low temperature without the cross-linking temperature that was the curing temperature that was usually supposed to be necessary to make that. And in vial 4, that was the final mixture with the heating and with an excess of the oligomer to be sure that whatever we took in that mixture, which cross-linker, accelerator, whatever, that a reaction should take place. Well, if you look at the expected compounds, you can see in the center of that circle that those are the compounds we try to react anyway. That is the rubber oligomer, and reacted that with a number of proposed ingredients of a rubber production mixture. And we simply reacted per type of reaction. We tried simply to compare if something would happen. This is another example what can be done. So in the first line there, you can see what we put together. Mixtures of those. On the left side, it's the C13 oligomer. On the right side, it's the C21. We simply mixed it and followed the instruction of the 4 vial strategy that I just explained. It's another example 2, with the sulfur instead of the other target molecule, if you want, and with the same setup of the study. Outside of the scope of this program, of course, you can try that with many other compounds, but it's simply a question of time, money, and availability of the compounds that you want to use. Also, this one can be done, so there are many options to follow up the project that we started. Well, what are the analytical analysis that we used for that? So the GCMS, the normal GCMS, is the most appropriate if you simply do a screening analysis. In the line 3, with the UPLC HRAM exactive orbit trap, that's the method we use for the LC screening analysis normally. The GC-QTOF methods, they are more for dedicated analysis, meaning that if you find something, you can make some kind of confirmation of that, what we want to see. Anyway, first step was that coming to the results already. First, what we want to see is, are the reaction conditions, are they okay? Do the vulcanizers disappear after the reaction? Are new compounds being formed? Meaning, are the reaction conditions okay? The next step would be, are there different differential peaks formed after curing? Differential peaks meaning, if you compare the chromatographs and if you see is there some additional peak that can be assigned to some reaction product. And the last step, of course, could other vulcanization reaction products be in there that were not expected? So this is the first example what we did, and that means that we compared the mixture of one of those compounds that were in our test system, and together with on the upper line that was compared to the mixture. And the first idea was, did that peak of the accelerator down in that on the downside, will that disappear during the reaction? And if you see there, well, it's completely disappeared after the reaction. That's no problem. The conditions were at least good enough to let them react. The next one is a bit more difficult to see. That's the reaction of the oligomer mix with the sulfur. And what you see is that there is a little peak of sulfur before the reaction, but that's still in there in the upper chromatogram, but you can't simply see it. But if you extract that ion that are for the sulfur, that this reaction is not completely done, so that you will have some remainders, not very good visible up in the upper chromatogram, but it's still there. This one is another example of differential peaks in the mixture before and after the reaction. Meaning the reaction in this case, it's before and after the curing. And what we can see is that there are some peaks that are added to the original chromatogram that is down. And those peaks there, those are the most interesting for us, of course, because something new came up. The next would be to identify them. And as you can see in the number 1, 2, 3, well, those are degradation products. But in number 4 and 5, those are the compounds that we expected. And if you see, those compounds would be expected if you react that starting compound, that TMTD, with the rubber oligomer, and that's some kind of a confirmation of our idea that could have happened. Of course, there's something else that was detected, and that is simply that not only the expected reaction takes place, but also it can react with another compound. In this case, it's formed the 2 peaks of the fatty acids that were still in the mixture, and that also could react in a quite similar reaction. Well, So those structures or those identities were confirmed later on with the GCQ turf. I will explain that later a bit more. That's another example, meaning with another compound that should react together with the same starting mixture containing the rubber oligomers, but with slightly different, of course, reaction products. And as you see, there is something that is expected, that's in line 4, and some additional other compounds that could also come up during the reaction. And that was something not completely expected, but something that is from today's view, nothing really unexpected, let's say. And if you see, there are several other compounds that are quite similar to the other reaction, because the mixture is in some part similar as the reaction before. And so that was not really surprising to find them after the reaction. And also those compounds were confirmed by GCQ TOF. Well, another example, this reaction, the same conditions together with the rubber oligomer. So here we are. So the expected adducts were found, and also some side products that were not expected in the beginning, but later on we found that those are quite logic to find them in there. To give you another example, it's this one. And also this one can be confirmed by the analytical methods that we applied on that. Well, I want to tell you a bit more. Well, I'll first show you the complete pictures then. Well, what is the difference between what's the advantage of the GCQ turf is that you can find dedicated compounds or more selected compounds in that sense. What we originally found that were the screening methods, of course, and then it's not so easy to find them back or confirm the structures by that method. Well, to give you another example, that's essentially in the same results, but of course, you have to see that there are some different ways to detect them. Well, now we have to look a bit more on the different analytical methods that we applied. This one is a GCQ turf with an electron impact analysis, meaning a quite hard method, meaning you will find some more fragments than with the chemical ionization. And in this case, if you see the full chromatogram and you extract from that chromatogram the selected mass that you would expect, then you can find a certain peak on that chromatogram that is typical for that expected compound. Of course, that's no final proof, and for that reason, we went to the GCQ turf with the chemical ionization. And in this case, it's more that you find the parent ion, or better way to identify the parent ion, because it's not only the parent, you will have some typical adduct formation together with the gas methane that is used to improve the ion formation. And that is then typical for the compound or for the parent compound that you found. That's a better proof of the identification this way. Well, to give you another example, this is the expected mass that we were looking for. And there we find the confirmation with the chemical ionization spectrum. And another example that is here. And in principle, it's the same thing, that we made our reactions, we found the expected compounds, and we confirmed the parent ions or the parent compounds by the chemical ionization reaction. Okay. Well, going back to our first observation, the initial observation, why we started the project, we wanted to see if this compound would be there, and if we can confirm that. And if you go back to that first, or one of the first slides, and our prediction that this would be the product from the oligomer together with the crosslinker, and that was expected that it would completely fit. And now we were looking for some proof that we can reproduce that compound or that peak and that mass that belongs to it with the R&D mixtures, meaning is it not accidentally coincidence or whatever, that we can confirm our initial idea why we started that project. And what we've seen then, when going back to the exactive orbit trap method from the beginning, and we would expect that mass of 629 in APC plus, and we actually found a peak at that retention time, and with the mass that belongs to it, and we could by that way prove that exactly the same happened that we expected for that. Well, this structure is confirmed that way. But if we looked a bit more, more in detail, let's say, what else can be seen? If we expected the main mass, but there was also some other fragments in the other chromatograms that are at other retention times too. So if you look at those here, at that slide, you can see that not only the parent ion can be seen in APCI, but also some other fragments, let's say. This one with the mass of 449 is most probably the one that you can see on that picture, that can be or half reacted compound, but it can be also a degradation product that is not fully clear, of course. And the other one with smaller mass at 433, that is most probably something where one of the sulfurs is replaced by an oxygen. Well, that's other retention times, of course, because that are smaller molecules with different properties. Well, what is the conclusion for us? We were able to predict other compounds, and by this way we could de-risk the unknown issue if we could have some kind of a better identification of those compounds that we found in extractable study, going from unknowns to something that is at least a bit more classified, or classes, chemical classes can be assigned to those compounds. It makes it much easier for the toxicologist to make assessment on those compounds. Okay. We further could prove that that's a compound, that's in the last slides, that we could make the link between the unknowns in commercial projects with those compounds in the study, meaning we had made a proof by that way, and that our strategy to find and identify further compounds, that it was a good strategy that would work for other compounds as well. However, still there are many unknowns in rubber extractable studies that need to be identified. So those results were mainly produced by my colleagues, Pete Christians, who is our scientific director, and other people who were busy with either GC or LC methods and were very much busy with the interpretation of data. Then. Okay, if you have any questions, feel free. You'll see the email addresses and also at the end of both our presentations, maybe. Thank you.
Okay, thank you very much for that presentation, Lothar.